Welcome all. This video is a continuation of the previous one which dealt about the introduction to the quadratic equations. In here, we are going to deal with solving a quadratic equation by completing the square. I am going to use the standard term instead of an example so that it's much easier for the next concept to come on. For the method of completing the square, you have to convert this equation to a form of your simple a plus b the whole square is equal to a square plus 2ab plus b square. You have to somehow bring this standard equation over here. Keeping that into mind, let's bring up stuff so that this equation is converted to this formula. For that, I'm going to multiply 4a over the whole equation so that I get a square as well over here. So multiplying 4a all over the equation, on both the sides. So 4a into 0 is obviously 0, so I have directly written 0. Opening the square, it should be 4a square x square plus 4abx plus 4ac is equal to 0. As you can see, this is in the form of a square and 2ab, but we need a b square. For that, we are going to add and subtract b square. So if you add and subtract b square on the same time, it equates to be 0. So there is no change in the whole equation. So 4a square x square plus 4ab x plus b square minus b square plus 4ac is equal to 0. So you can see that this is in the form of a square plus b square plus 2ab, which is equal to a plus b the whole square. So it turns out to be 2ax plus b the whole square minus b square plus 4ac. I hope you can see that we have converted this equation ax square plus bx plus c somehow into this formula, and it turns out to be 2ax plus b the whole square minus b square plus 4ac is equal to 0. Now you can see that it has completed a square and you can easily solve for x. For the next step, we are going to take these two terms to the next side. It becomes b square plus 4ac. Now apply square roots, which will give you 2ax plus b is equal to plus or minus square root of b square minus 4ac. For both these, because if you take these to the next side, it should be plus b square and minus 4ac. So it must be 2ax plus b is equal to plus or minus b square minus 4ac. It's plus or minus because a square root of a number can either be of a positive number or a negative integer. As if you square a positive or negative integer, the square will be a positive integer somehow. So this will equate to be 2ax is equal to minus b plus or minus root b square minus 4ac. So x is equal to minus b plus or minus root of b square minus 4ac by 2a. So this is your solution for the equation ax square plus bx plus c is equal to 0. And you have two solutions. One is minus b plus b square minus 4ac the whole root by 2a, and the other will be minus b minus root of b square minus 4ac the root by 2a. So you have two solutions, and if you can see, we have derived it from a standard form. So this is called as a quadratic formula. You can use this formula to derive at solutions of a particular quadratic equation. Having derived at the quadratic formula from the standard form of ax square plus bx plus c is equal to 0, we are going to see the next term, that is a discriminant, which is termed as d is equal to b square minus 4ac. You call it as a discriminant because it is nothing but the term over here under the square root, and it is used to determine the nature of roots, whether they are real roots or whether they are imaginary roots. So if b square minus 4ac is greater than 0, the roots obtained are two distinct real roots. That is, the roots are real and they are unequal. Whereas if b square minus 4ac is equal to 0, it says that these are two equal real roots. And if b square minus 4ac is less than 0, these are not real roots. These are called as imaginary roots. You call it as imaginary because imaginary numbers are nothing but numbers with minus under a square root. For example, minus 1. It has no real value, so it's called as a imaginary root, and it is equal to I. We'll get to know more about it in the upcoming chapters. I hope you like the video. If you have any doubts, please share in the comments. Thank you.